These are the 8 things physicists actually know about how the universe ends, and every single one of them is already unfolding, in painfully slow motion, right now, while you watch this. This is the calm science of the end of everything, and by the time we're finished, you'll understand exactly what's coming, roughly when it's coming, why scientists are still arguing about which ending is the real one, and why none of it needs to keep you up tonight. If long, quiet deep dives into real science help you unwind rather than spike your anxiety, stay a while, and consider liking this video and subscribing, because we're going to be spending a lot more time out here, at the edge of what's actually known. Let's start with where we are, because that single number tends to rearrange a person's whole sense of scale before we've even gotten to the interesting part. The universe is about 13.8 billion years old. Astrophysicists Fred Adams and Gregory Laughlin, who spent years mapping the far future of the cosmos in a book called The 5 Ages of the Universe, measure time using something they call cosmological decades, where each decade simply means 10 times as many years have passed since the Big Bang. On that scale, we're living early in cosmological decade 10. That sounds unremarkable until you learn where the scale eventually goes. Decade 30, decade 60, decade 100, and further still. We are not in the middle of this story. We're barely past the first page, and as far as anyone can tell, the book doesn't have a fixed number of pages at all. Here's the part that tends to genuinely surprise people. Physicists don't actually agree on how the story ends. There isn't one accepted apocalypse, the way there's one accepted age for the universe. There are several competing endings, each one resting on real measurements, real equations, and real open questions that haven't been settled. Dr. Katie Mack, a theoretical astrophysicist who has spent much of her career thinking about exactly this question, wrote an entire book laying out 5 of the leading possibilities: the Big Crunch, heat death, the Big Rip, vacuum decay, and something called the bounce. Mack has said she became fascinated with the subject as an undergraduate, when an astronomy professor casually mentioned that the universe could end at any moment, without warning, and that single offhand comment set her on the path toward theoretical astrophysics. That's the tone we're going for tonight. Not dread, curiosity. The universe is going to do something, eventually, and physicists have actually narrowed the shortlist down quite a bit. But before we get to the big finales, we need to walk through everything that happens first, because the ending of everything is preceded by an extraordinarily long, strange middle chapter, and a surprising amount of it is closer to home than you'd expect. Section 0. We are not the first to wonder. Before we get into the physics, it's worth pointing out something that tends to get lost in videos like this. Humans have been trying to answer this exact question for as long as we have written language, and the honest answer is that watching how differently every culture has imagined this moment tells you almost as much about people as the physics tells you about the universe. Take the Norse. Their version, Ragnarök, comes down to us mainly through 2 medieval texts, the Icelandic poem Völuspá and Snorri Sturluson's 13th century prose Edda. It opens with 3 consecutive years of brutal winter and no summer between them, called Fimbulvetra. Then the wolf Skjöll finally catches and swallows the sun. Its counterpart, Hati, catches the moon. The stars simply vanish. The earth shakes so violently that every bond and restraint in the world snaps loose, and the dead themselves rise up. Loki leads an army of giants against the gods in one final battle, and in it, major figures die on both sides: Odin, Thor, Freya, Loki himself, before the entire world sinks beneath the sea. Most of the versions that survive describe the world eventually resurfacing afterward, repopulated by 2 human survivors, though scholars studying this genuinely disagree about whether that hopeful ending was part of the original pre-Christian belief, or whether it was added later, since every surviving text was written down by Christian or Christian-influenced scribes. Some researchers have even pointed out that the imagery, darkened skies, the ground trembling, closely resembles what a severe volcanic eruption actually looks like on the ground, suggesting the myth may have grown out of real, remembered natural disasters. Now compare that to Hindu cosmology, which doesn't really have an ending at all, in the way we usually mean that word. Time moves in enormous, repeating cycles. A single day in the life of the creator god Brahma, called a kalpa, lasts 4.32 billion years, and it's followed by an equally long night, called a pralaya, during which the universe simply rests in dissolution before starting again. Brahma's entire lifespan adds up to 100 of his own 360-day years, which works out to roughly 311 trillion years, at the end of which the whole universe dissolves completely, and an entirely new Brahma begins a fresh cycle from scratch. Inside each of those enormous days, smaller ages called yugas play out, 4 of them, each one shorter than the last, each one marked by a little more moral decline than the one before it. We're currently believed to be living inside the 4th and final one, the Kali Yuga, said to have begun back in 3102 BCE. It's genuinely worth sitting with how naturally that entire framework, vast cyclical ages, expansion followed by dissolution followed by expansion again, echoes the cosmological decades we've spent this whole video walking through, even though one of these systems comes from ancient religious cosmology and the other comes from particle accelerators and orbiting telescopes. Buddhist cosmology builds on that same idea of the kalpa, but aims it somewhere slightly different. Rather than offering a specific numerical answer for exactly when things end, it uses cyclical time mainly to illustrate a broader point, that everything, including the universe itself, is fundamentally impermanent. One old passage from the Pali Canon, part of the earliest surviving Buddhist scripture, describes the eventual end of a given world through the gradual appearance of extra suns in the sky. First one, drying up rain and vegetation, then another, evaporating the rivers and lakes, and so on, escalating sun by sun, until the earth itself is finally destroyed. It's a slow-motion apocalypse by increasing heat, oddly reminiscent, in its shape if nothing else, of a red giant sun consuming a solar system from the inside out. And crucially, Buddhism doesn't treat this as a single final judgment the way some other traditions do. It's just one destruction and renewal cycle in an ongoing, unending series, tied to the same broader concept of endless cyclical rebirth that runs through the rest of Buddhist thought. Then there's a tradition that comes from an entirely different direction, Greek and Roman Stoic philosophy. The Stoics believed in something called ekpyrosis, a Greek word meaning conflagration, the idea that the entire universe periodically dissolves completely into fire, only to reform out of its own ashes and start again. Some trace the root of the idea back to the early philosopher Heraclitus, around 500 BCE, though scholars still actively debate how much of the fully developed version genuinely traces back to him versus later Stoic thinkers. Chrysippus, the most influential Stoic philosopher, is associated with an especially intense version of the idea that after each conflagration, the exact same events play out again, identically, down to the smallest detail, the same people living the same lives in the same order, over and over, forever. And importantly, the Stoics didn't see any of this as a tragedy. The fire itself was identified with the Logos, a rational, ordering principle they believed ran through the entire universe, so the conflagration wasn't really destruction at all, in their eyes. It was purification. One modern historian describing this idea for a general audience put it plainly: it's a lot like the Big Crunch. Zoroastrianism, the ancient Persian religion founded by the prophet Zoroaster, takes the opposite approach entirely. Where the Norse, Hindu, Buddhist, and Stoic pictures are all, in their own ways, cyclical, repeating forever, Zoroastrianism is strictly linear. History unfolds across a single 12,000-year arc, divided into 4 equal ages, and it's explicitly heading toward one final, positive conclusion, called frashokereti, which roughly translates to making wonderful. At the very end, according to the tradition, a savior figure is born, the dead are physically resurrected, and all of humanity passes through a flood of molten metal that the already righteous experience as something like warm milk, while it burns away whatever evil remains in everyone else. Evil itself, personified as the spirit Angra Mainyu, is destroyed completely and permanently, and the world becomes perfect, deathless, and eternal, forever. Some scholars have proposed, though this remains a genuinely debated historical question rather than settled fact, that ideas like these may have influenced later Jewish, Christian, and Islamic concepts of resurrection, final judgment, and a linear history heading toward a definite ending, given the real historical contact between Zoroastrian Persia and the Jewish community during and after the Babylonian exile. Halfway around the world, with no possible contact between the two civilizations, the Aztecs independently arrived at their own version of repeating catastrophic world ages, recorded in Nahuatl texts and famously carved into the enormous Aztec sunstone. In their account, 4 previous worlds, or suns, had already been created and violently destroyed before our own. One ended when its people were devoured by jaguars, one was torn apart by hurricanes, one was consumed by a rain of fire, and one drowned in a catastrophic flood, with the survivors of each transformed into monkeys, birds, or fish, depending on the disaster. We're currently living, according to this tradition, inside the 5th sun, created through the self-sacrifice of the gods themselves at the ancient city of Teotihuacan, and this era is specifically prophesied to end in catastrophic earthquakes. What's genuinely striking is what the Aztecs did with that belief. Rather than treating the coming destruction as something to simply await, they treated ongoing ritual and sacrifice as a way of actively delaying it, a kind of continual payment required to keep the current cosmic order running just a little longer. And then there's the example that might be the single best illustration of how easily any of this can get distorted once it leaves its original context: the Maya long count calendar, and the entire world ends in 2012 scare that briefly gripped a huge chunk of the planet. The long count genuinely does count continuously from a mythical creation date corresponding to August 11th, 314 BCE, using a unit called the Baktun, roughly 394 years long, and December 21st, 2012, genuinely did mark the completion of the 13th Baktun on that calendar. Both of those facts are real, well documented, and not disputed by scholars in the slightest. What isn't real is the idea that any known Maya inscription actually describes that specific rollover as the end of the world. Maya epigraphers, researchers who specialize in actually reading the hieroglyphic inscriptions, have pointed out that the calendar simply continues past that date into a new count, the same way a car's odometer rolls from 999,999 back to all zeros, without the car itself ceasing to exist. The next larger calendrical unit up from the Baktun wasn't even due to complete for another roughly 2,700 years past 2012. The doomsday interpretation was, in large part, a modern invention, layered on top of a perfectly ordinary calendrical transition by people working outside the actual Maya scholarly tradition, and it's a genuinely useful cautionary example to keep in your back pocket for the rest of this video, because it shows exactly how an accurate underlying fact, real calendar, real completed cycle, real ancient astronomical sophistication, can get inflated into an apocalypse that the original source never actually described. Here's what's worth carrying forward from all of that into the rest of this video. Every single culture that's ever looked up at the sky and thought carefully about time has landed on some version of an ending, or a repeating cycle of endings, whether that's gods dying in Scandinavian ice and fire, an endless wheel of Brahma's cosmic days and nights, a slow apocalypse by accumulating suns, a purifying conflagration according to Greek philosophers, a single triumphant renewal according to Persian prophets, 5 successive suns requiring constant ritual maintenance according to the Aztecs, or a calendar wheel that modern audiences briefly, mistakenly, decided was a prophecy. None of that makes the specific religious or mythological content of any of these traditions true or false. That's simply not a question this video is set up to answer, and it's worth being clear about that. But it does tell you something real and worth sitting with. The impulse to ask, how does this end, appears to be close to a universal human trait, one that shows up independently across cultures that had no contact with each other whatsoever. What's genuinely different about the version we're about to walk through for the rest of this video isn't the impulse behind it, it's the method. Instead of prophecy, revelation, or philosophical inference, what follows is built entirely on measurement. Particle detectors a kilometer underground, space telescopes scanning for a specific wavelength of gamma ray, and a 5,000-eyed instrument on a mountain in Arizona. All of it checkable, all of it revisable, the moment better data comes in. That's the thread connecting everything from here forward. Section 1. What happens to us, specifically? Our Sun is a fairly ordinary middle-aged star, sitting roughly halfway through the hydrogen-burning phase of its life. In about 5 billion years, it will exhaust the hydrogen fuel in its core, and it will begin to swell into what astronomers call a red giant. When that happens, Mercury and Venus are expected to be engulfed and destroyed outright, swallowed by a star that, by then, will have grown far larger than the orbits those two planets currently occupy. For a long time, the working assumption was that Earth would share that same fate, dragged inward and consumed right alongside its smaller neighbors. That picture has actually shifted recently, and it's a good early example of how alive this field of research really is. A new study, using updated models of how gravitational tidal forces actually behave between an aging star and its planets, found that the forces dragging Earth toward the expanding Sun are weaker than older calculations had assumed. Under this newer modeling, Earth, and possibly Mars as well, may have a genuine chance of drifting slowly outward and surviving the Sun's expansion rather than being swallowed by it. That's the encouraging part. The less encouraging part is that surviving physically and staying habitable turn out to be two very different things. Even in the version of events where Earth escapes being engulfed, its surface would still become completely hostile to any life we'd recognize today, because surviving here just means still technically existing as a rock in orbit, not still pleasant to live on. So somewhere around 5 billion years from now, whether or not the physical planet Earth survives, the era of Earth as anyone's home comes to a close. And it's worth pausing on that timeline for a second, because 5 billion years is an enormous number, but it isn't an unfathomable one. It's smaller than the age of the universe itself. Whatever else eventually happens to the cosmos as a whole, our own solar system's story wraps up relatively early, while the rest of the universe is still, in cosmic terms, just getting started. Meanwhile, something else has been quietly closing in on us for a very long time. The Andromeda Galaxy and our own Milky Way are currently about 2.5 million light-years apart, and they're moving toward each other at somewhere around 400,000 kilometers per hour, pulled together by gravity, the way any two massive objects sharing a gravitational field eventually are. Most estimates put the eventual collision somewhere between 4 and 4.5 billion years from now, which means, strikingly, that it lines up almost exactly with the Sun's own transformation into a red giant. By the time our Sun is swelling into its final phase, the sky above whatever's left of Earth may already be filled with the enormous, gradually brightening smear of an incoming galaxy. Here's a detail that tends to ease people's minds once they actually hear it. Even though we call it a collision, individual stars almost never physically hit each other. Stars are so widely spaced, even within a densely packed galaxy, that when two galaxies merge, it's overwhelmingly likely that every single star passes cleanly through the wreckage without ever touching another star directly. What actually collides isn't stars, it's structure. Vast clouds of interstellar gas get compressed together and spark bursts of new star formation. Orbits get scrambled and redrawn. Over the course of a few billion years, two spiral galaxies gradually lose their distinct pinwheel shapes and settle into a single, larger elliptical galaxy, a merged object that astronomer Avi Loeb, one of the researchers who modeled this collision in detail, nicknamed Milkomeda. And now, the twist that makes the whole thing feel a little less certain than it used to. In June of 2025, a new round of computer simulations, this time factoring in the gravitational pull of other nearby galaxies within what's called the local group, suggested the Milky Way-Andromeda collision might not be the sure thing astronomers have long assumed. One report on the findings described the revised odds as basically a coin flip. That's worth sitting with for a moment, because it's a genuinely good example of how this entire subject actually works. These aren't ancient myths carved into stone somewhere. They're live scientific models, built on the best currently available data, and they get revised the moment better data comes in. The collision that seemed inevitable a decade ago is, as of the most recent modeling, closer to 50-50. Section 2. The Long Twilight of the Stars. Let's zoom out now, well past our own solar system, because the universe as a whole is going to keep going, in one form or another, for a length of time that makes 5 billion years look like nothing at all. Right now, we're living inside what Adams and Laughlin call the stelliferous era, which simply means filled with stars. It's the era of galaxies, active star formation, planets, and, as far as anyone currently knows, the only era in which life like ours has ever existed anywhere. It began a few 100 million years after the Big Bang, and it's expected to continue for an almost incomprehensibly long stretch of time after we're gone. The largest, brightest stars burn through their fuel quickly, in cosmic terms, lasting mere millions of years before exploding or collapsing entirely. But the smallest stars, the dim, slow-burning red dwarfs, are far more patient than that. These stars ration their fuel so efficiently that some of them are expected to still be shining, faintly, 10 trillion years from now, long after every sun-like star in the universe has already gone dark. Eventually, though, even they run out. The stelliferous era doesn't end with any kind of bang. It ends quietly, with galaxies gradually running out of the raw hydrogen gas needed to build new stars in the first place, and the very last red dwarfs slowly, gently fading into darkness. By the time that finally happens, the universe will be roughly 100 trillion years old, marking the boundary of what Adams and Laughlin call cosmological decade 14. Try to actually hold that number for a second. 100 trillion years. The universe today is 13.8 billion years old. If the entire history of the universe up to this exact moment were compressed into a single calendar day, the point at which the very last star flickers out wouldn't even register as a rounding error. That's how far in the future it sits. And yet it's still, relatively speaking, early. Everything we've discussed so far, the sun's death, the galaxy collision, even the slow fading of the very last star in existence, happens well before the universe reaches what Adams and Laughlin consider the truly deep future. There's one more consequence of an accelerating universe worth introducing here before we go any further, because it changes something fundamental about what future observers will even be able to know. Physicists Lawrence Krauss and Robert Scherer published a paper in 2007 titled The Return of a Static Universe and the End of Cosmology that won a top prize that year from the Gravity Research Foundation. Their central finding, because dark energy keeps accelerating the universe's expansion, every galaxy outside our own small cluster, our local group, is eventually going to cross what's called our cosmic horizon, the boundary past which light simply can never reach us again, because the space between us and that galaxy is stretching faster than light itself can cross it. Krauss and Scherer calculated that within roughly 100 billion years, every galaxy beyond the local group will have redshifted so severely that it becomes permanently undetectable. What remains, visible to any future observer looking out from our galactic neighborhood, will be what the researchers called an island universe, the Milky Way and its handful of close companions, adrift alone inside an overwhelmingly dark, empty-looking void. Push the clock forward further, to around 10 trillion years, and the redshift of anything beyond that local group reaches a genuinely absurd value, somewhere around 10 to the 53rd power, at which point even the highest energy cosmic rays arriving from outside will have stretched away into nothing. Here's the detail that makes this genuinely unsettling rather than just abstractly large. Even the cosmic microwave background itself, the faint afterglow radiation left over from the Big Bang, and one of the strongest pillars of evidence we currently have for the Big Bang model, will eventually redshift to wavelengths so long that it becomes physically undetectable from within our galaxy. Krauss put it bluntly, we literally will have no way to detect this radiation. Once the universe is about 25 times its current age, that microwave background will have stretched past the point where it can even penetrate our galaxy's interstellar gas. Which means that any civilization, any scientist, any curious mind living in our galaxy tens of billions of years from now, doing careful, honest, rigorous science with every tool available to them, would very reasonably conclude that they live inside a single, static, eternal galaxy, surrounded by empty space, with no Big Bang, no expansion, and no larger universe beyond it at all. Krauss and Scherer wrote it plainly in their own paper. While physicists of the future will be able to infer that their island universe has not been eternal, it is unlikely they will be able to infer that the beginning involved a Big Bang. They would be doing everything right, and they would still, through no fault of their own, land on a picture of the cosmos that is completely, confidently wrong. Later science writers have pointed out that the real significance of this finding isn't really about the far future at all. It's about the reliability of observation itself, here and now. If an entire era of careful, intelligent observers could be doomed to a confident and completely mistaken picture of the universe, simply because the evidence they'd need had already drifted permanently out of view, the obvious follow-up question is uncomfortable. What, if anything, might we already be missing right now, in this narrow and finite window, when the evidence still happens to be visible? Section 2.5. The faint glow that proves all of this. Before we go any further into the deep future, it's worth pausing on something happening right now, tonight, because it's the actual physical evidence underneath almost everything we've said so far, and the story of how we found it is oddly charming for something this important. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, using a sensitive horn antenna that had originally been built to communicate with early Telstar satellites. When that satellite work wound down, they repurposed the antenna for radio astronomy and immediately ran into a problem: a faint, persistent hiss of noise coming evenly from every direction in the sky that they simply could not get rid of. They spent months chasing it down. They checked the wiring. They pointed the antenna at New York City to rule out human interference. At one point, they found a pair of pigeons that had taken up residence inside the antenna horn, evicted them, cleaned out the mess the pigeons had left behind, and the noise was still there. It took contact with a separate group of physicists at Princeton, who were independently building an entire theoretical case that the early universe should have left behind exactly this kind of faint, uniform radio hiss, for Penzias and Wilson to realize what they'd actually stumbled onto: the afterglow of the Big Bang itself, redshifted by billions of years of cosmic expansion into a very faint microwave signal. They received the Nobel Prize for it in 1978. That signal is called the cosmic microwave background, and it's still out there right now, arriving from every direction in the sky at once, measured today at a temperature of 2.725 Kelvin, just a couple of degrees above absolute zero. When it was first released, roughly 380,000 years after the Big Bang, at the moment the early universe finally cooled enough for electrons and protons to combine into neutral atoms and stop scattering light like a thick fog, this radiation was blazingly hot, somewhere around 3000 Kelvin. 13.8 billion years of cosmic expansion has since stretched its wavelength by a factor of roughly 1100, cooling it the entire way down to the faint microwave hiss Penzias and Wilson accidentally picked up decades ago. It's remarkably uniform across the entire sky too, varying by less than 1 part in 10,000 once you subtract out our own galaxy's motion. And that extreme uniformity is itself one of the major pieces of evidence supporting cosmic inflation, the theory describing the universe's extraordinarily rapid expansion in its first fraction of a second. We're bringing this up here, in the middle of a conversation about the far future, for a specific reason. This is the exact same radiation we mentioned earlier, the one Krauss and Scherer calculated will eventually redshift beyond detectability from within our own galaxy, tens of billions of years from now. Right now, tonight, we are living inside a universe where this signal is still detectable, still measurable, still actively confirming the Big Bang for anyone with the right antenna. That won't be true forever. We are, in a very real sense, standing inside a finite window where the direct fingerprint of our universe's origin is still visible, and that window is, cosmically speaking, closing. Section 3. The Degenerate Era and the Strange Physics of Proton Decay. Once the last star finally goes dark, the universe doesn't become empty. It becomes something stranger, a graveyard of stellar remains, made up of white dwarfs, neutron stars, brown dwarfs that never quite ignited in the first place, and black holes, all drifting through an increasingly dark and increasingly cold universe. Adams and Laughlin call this the Degenerate Era, running from roughly cosmological decade 15 out to decade 39. The name has nothing to do with morality, by the way, despite how it sounds. It's borrowed directly from quantum mechanics, describing a particular state of extremely compressed matter, the kind you get when gravity crushes an object until quantum effects, rather than heat, are the only thing left holding it up against total collapse. Part of what fills this era is a slow, ongoing process of planets getting stripped away from whatever's left of their stars. And this isn't a purely speculative leap. It's an extrapolation of something astronomers already watch happening today. Modern surveys using gravitational microlensing, techniques with names like OGLE, MOA, and KMTNet, have already found real evidence for so-called rogue planets, worlds with no host star at all, drifting alone through the galaxy. Current estimates suggest there may be roughly one Jupiter-sized rogue planet out there for every few stars in the Milky Way, and smaller, Earth-sized rogue worlds may be considerably more common still. The James Webb Space Telescope has even directly imaged pairs of these starless, planet-sized objects orbiting each other with nothing else around them at all. The mechanism that creates them is well understood. Violent gravitational interactions, whether between competing planets in a young system or close encounters with a passing star, can fling a world clean out of its own solar system, sometimes after bouncing through dozens or even hundreds of additional close gravitational encounters with other stars and planets before it finally escapes for good. Adams and Laughlin simply take that same, already observed mechanism and run it forward across the degenerate era's much longer timescale, as dying stars and drifting planets keep tugging at each other, gradually scattering worlds loose from whatever gravitational grip remains. For a long stretch of this era, some of these dead stars keep generating a faint trickle of energy by slowly consuming stray dark matter particles that happen to wander too close, but that particular source of fuel dries up by around cosmological decade 30. It's worth pausing on that phrase, dark matter particles, because it's doing a lot of quiet work. Dark matter is estimated to make up somewhere around a quarter of the entire universe's total mass and energy, several times more than all the ordinary matter making up every star, planet, and person put together. And physicists know it exists purely because of its gravity. It bends light passing near galaxy clusters. It makes stars orbit their galaxies faster than the visible matter alone could explain. It shapes how entire clusters of galaxies collide and pass through one another. And yet, despite decades of dedicated searching, using giant underground detectors, particle accelerators, and purpose-built experiments with names like the Axion Dark Matter Experiment, nobody has ever directly detected a single dark matter particle in a laboratory. The two leading theoretical candidates, heavier particles called WIMPs, and much lighter, more exotic particles called axions, have both been hunted for years, and both searches have, so far, come up empty. So when Adams and Laughlin describe dead stars slowly feeding on dark matter deep into the degenerate era, they're extrapolating forward from our best current theories about a substance that, right now, in the present day, we still can't directly identify. It's a reasonable, serious scientific assumption built on real gravitational evidence, but it's also a genuine reminder of how much of this entire subject rests on filling in blanks that are still, quite literally, blank. After that point, the only thing left keeping these objects from becoming completely inert is a process so slow and so deeply strange that physicists haven't even confirmed it actually happens yet: proton decay. Here's what we actually currently know. In the plain, ordinary standard model of particle physics, protons are treated as perfectly, permanently stable, full stop. But many of the more ambitious theories that try to unify the fundamental forces of nature, the so-called grand unified theories, predict that protons aren't actually stable at all. They just take an unimaginably long time to fall apart. And unimaginably long isn't a figure of speech here. It's the literal, technical description. The leading experiment hunting for this is called Super Kamiokande, a 50,000-ton water tank built about 1,000 meters underground, inside the Kamioka mine in Japan, purpose-built to catch the extraordinarily rare flash of light a single decaying proton would theoretically produce. Decades of patient, careful watching, and Super Kamiokande has never once caught a proton in the act. What it has produced instead is a growing series of lower limits, each one longer than the last. As of the most recent published results, the proton's lifetime, for one particular decay pathway, has to be longer than 1.4 times 10 to the 34th years. For another pathway, it has to be longer than 7.3 times 10 to the 33rd years. To put that in perspective, those numbers are already roughly 10 trillion times longer than the entire current age of the universe, and we still haven't caught it happening even a single time. Physicists keep building bigger, more sensitive detectors, hoping to eventually catch it, because if protons really do decay, it changes the long-term chemistry of absolutely everything. Eventually, given enough eons, even the atoms locked deep inside dead stars would simply dissolve, one particle at a time. If that decay really is happening, then by the end of the degenerate era, the white dwarfs and neutron stars that made up the last visible structure in the universe will have slowly converted themselves into pure radiation as their protons and neutrons quietly fall apart, one at a time, across spans of time that dwarf almost every other number in this video. And here's a figure that tends to get a genuine reaction out of people. A white dwarf powered purely by that trickle of proton decay would put out only about 400 watts of total energy. 400 watts. That's dimmer than some ordinary kitchen appliances. An entire galaxy full of these fading, dying stars would together be less luminous than a single ordinary sun. That's the practical endpoint of the degenerate era. Not total darkness exactly, but a light so faint it barely qualifies as light at all anymore. Section 4. The Black Hole Era. After the degenerate era finally winds down, somewhere around cosmological decade 39, almost nothing is left except black holes. Not because black holes are somehow immune to decay, but because they take even longer to disappear than anything else the universe has to offer. This is where Stephen Hawking's most famous contribution to physics becomes the whole story. In 1974, Hawking showed that black holes aren't perfectly, permanently black after all. Once you combine quantum mechanics with general relativity, black holes turn out to emit a very faint stream of radiation, now called Hawking radiation, and in doing so, they very slowly lose mass over time. Given enough time, they evaporate completely, down to nothing. How much time depends entirely on how big the black hole is, and the relationship runs backward from what most people would expect. Bigger black holes are actually colder, and colder black holes evaporate more slowly, not faster. A black hole with roughly the mass of our Sun would take about 10 to the 67th years to fully evaporate. The supermassive black holes sitting at the centers of galaxies, the truly enormous ones, are expected to take somewhere between 10 to the 90th and 10 to the 100th years, a figure commonly nicknamed a Google years, a 1, followed by 100 zeros. Yale astrophysicist Priyamvada Natarajan, who studies black holes for a living, put that scale into words better than most people could manage. The entire age of the universe, she's noted, is a fraction of the time it would take for one of these giants to evaporate. As far as we're concerned, she says, it is eternity. And there's a strange upside buried inside that physics. Because bigger black holes evaporate more slowly, growing larger is, in a very literal sense, a way for a black hole to postpone its own ending indefinitely. Astronomer Shepard Doleman has described this as a black hole's ability to cheat death, quite simply, by growing. Physicists have gone looking for direct evidence of black holes actually finishing this entire process, since the underlying theory predicts a final, intense burst of gamma rays in an evaporating black hole's very last moments. NASA's Fermi Gamma Ray Space Telescope has spent years scanning the sky specifically for that exact signature. So far, nothing has turned up, which honestly isn't surprising, once you remember the timescales actually involved here. Even the smallest realistic black holes we currently know about are expected to significantly outlast the entire current age of the universe. We simply aren't far enough along in cosmic history to have witnessed even a single one finish evaporating. On any timescale a human civilization could realistically track, we may never be. Section 5. The Dark Era. Eventually, though, even the supermassive black holes finish the job. Once the very last one evaporates, somewhere around cosmological decade 100, the universe enters what Adams and Laughlin call the Dark Era. There isn't a dramatic name attached to what's left, mostly because there isn't much left to name at all. No stars, no black holes, no stellar remnants of any kind, assuming proton decay has run its full course by then. just an extraordinarily thin, extraordinarily cold scattering of light particles, and, possibly, a handful of exotic leftover particles, spread across a universe that has, by this point, been expanding for longer than any single number in this video could really convey, in a way that feels intuitive. The authors of The 5 Ages of the Universe speculate about a few strange, low-energy processes that might still play out even this far into the future, and even raise, somewhat philosophically, the possibility of some kind of renewal, a new universe, somehow emerging from the ashes of the old one. But by any ordinary definition of activity, motion, or event, this is about as close to a true, final full stop as physics currently lets us imagine. That's the story if nothing unusual interrupts it. But here's the twist we mentioned right at the very beginning. This slow fade to black, spread across a Google years, is only one of several genuinely possible endings, and some of the others could arrive far, far sooner, or, in one particular case, without giving us any warning whatsoever. Section 5.5, where the idea of entropy actually came from. Before we get to heat death itself, it's worth backing up about 200 years, because the idea didn't start with anyone looking at the stars at all. It started with steam engines, and it started with a young French military engineer who died forgotten at 36 of a disease that caused the authorities to burn most of what he'd ever written. His name was Sadi Carnot, and in 1824, at the age of 28, he published the only book he would ever write, a slim volume called Reflections on the Motive Power of Fire. France, at the time, was falling behind Britain industrially, and Carnot, convinced that his country's underuse of steam power was part of the problem, set out to answer a deceptively simple question: how efficient could a steam engine possibly be, in principle, no matter how well built? His answer turned out to be one of the most important ideas in the history of physics. He realized that useful work only comes out of a heat engine when heat drops from a hotter place to a colder one. In the same basic way, water only turns a water wheel while it's actually falling from high to low, and that the maximum possible efficiency of any engine depends purely on the size of that temperature drop, nothing else. That single insight, now called the Carnot cycle, effectively founded the entire field of thermodynamics. It received almost no attention while Carnot was alive. He died 8 years later, in 1832, during a cholera epidemic that swept through Paris, and because cholera was considered contagious at the time, the authorities burned most of his belongings after his death, including unpublished manuscripts. A handful of pages survived anyway, and when historians finally examined them, decades later, they showed Carnot had already begun quietly questioning the leading theory of heat of his own era, and had anticipated ideas that wouldn't be properly worked out by anyone else for another 20 years. It took a German physicist named Rudolf Clausius to turn Carnot's insight into the modern language of entropy. Clausius spent 15 years, from 1850 to 1865, reworking Carnot's results mathematically, and in 1865 he did something almost startlingly casual. For an idea this consequential, he simply invented a new word for the quantity he'd been calculating. He wanted a name that would work the same way in every modern language, so, by his own account, he went looking in ancient Greek and landed on the word trope, meaning transformation, deliberately built to echo the word energy, since he considered the two quantities so closely related. That's it. That's where the word entropy comes from, a single, calculated act of scientific naming, less than a decade before Charles Darwin's ideas were already reshaping biology, less than a decade after the American Civil War, at a level of scientific maturity that could already describe the eventual fate of the universe using precise mathematics. And Clausius didn't stop at naming the quantity. In that very same 1865 paper, he closed with 2 sentences that summarized both the first and second laws of thermodynamics, applied explicitly to everything, the whole universe at once, not just an engine in a laboratory. The energy of the universe is constant, and the entropy of the universe tends toward a maximum. That exact 2-line summary, written 160 years ago by a physicist thinking about steam engines, is, word for word, the seed of everything we're about to describe as heat death. Meanwhile, a separate line of research was proving that heat and mechanical energy were actually the same thing, just in different forms, and the person who nailed that down was an English physicist named James Prescott Joule, who happened to be the son of a brewer, which meant he'd grown up around unusually sensitive thermometers. Joule's most famous experiment involved a descending weight, connected over a pulley to a paddle wheel, submerged in an insulated barrel of water. As the weight fell, the paddle churned the water, and the friction from that churning raised the water's temperature by a tiny, carefully measured amount. By comparing exactly how far the weight fell to exactly how much the water warmed up, Joule calculated a specific, numerical, mechanical equivalent of heat, a fixed amount of physical work that reliably produces a fixed amount of heat every single time. When he first announced his results, in 1843, at a scientific meeting, he was met with silence. Nobody quite grasped what he'd actually shown. It took years, and confirmation from several independent directions, gas compression, water forced through narrow tubes, before the scientific community came around to what's now considered one of the experimental pillars underneath the entire first law of thermodynamics, that energy, in all its forms, heat included, is conserved. Joule later teamed up with the physicist William Thomson, who would eventually become known as Lord Kelvin, and together they helped establish the absolute temperature scale still used today, the one where 0 degrees represents the coldest anything can theoretically get. And then, in 1867, the Scottish physicist James Clerk Maxwell threw a wrench directly into the whole picture, on purpose, just to see what would happen. In a letter to a colleague, Maxwell proposed a thought experiment. Imagine a box split into 2 chambers by a wall with a tiny door, and imagine a finite being, as Maxwell originally called it, standing at that door, able to see every individual gas molecule coming and going. This being could let fast, hot molecules through into one side and slow, cold molecules through into the other, without doing any physical work at all, apparently sorting a mixed, disordered gas into a hot side and a cold side purely through observation and perfect timing, seemingly creating usable energy out of nothing and quietly breaking the second law of thermodynamics in the process. Lord Kelvin later nicknamed this hypothetical being a demon, and the name stuck. It took roughly a century of careful follow-up work, from physicists including Leo Szilard, Leon Brillouin, and later Rolf Landauer and Charles Bennett, to fully resolve the puzzle. The demon has to store information about each molecule somewhere, in some kind of memory, and the act of eventually erasing that memory generates at least as much entropy as the demon appeared to save, which means the second law survives completely intact once you honestly account for the cost of the demon's own bookkeeping. That resolution turned out to be historically enormous in its own right, because it was the first serious, rigorous link ever drawn between physical entropy and information itself, a connection that runs in an unbroken line all the way to Claude Shannon founding modern information theory in 1948, and, more surprisingly, all the way to that reversible computing footnote we mentioned earlier regarding Freeman Dyson's proposal for eternal intelligence, since reversible computation is, at its core, exactly the kind of information processing Maxwell's demon would need to genuinely get away with cheating the second law. By the time Ludwig Boltzmann connected this entire body of work down to the actual, physical motion of individual atoms in the 1870s, the idea we've spent this entire video building toward, from Boltzmann brains to the Dark Era to heat death itself, was essentially already assembled, piece by piece, by a small handful of 19th century European scientists working with paddle wheels, brewery thermometers, and steam engine blueprints, decades before anyone had the faintest idea the universe itself was expanding, and more than a full century before anyone could measure a black hole, a proton's lifetime, or the mass of a Higgs boson. It's one of the more remarkable facts buried in this entire subject. The mathematics describing how the universe itself will eventually end was largely worked out by people trying to make steam engines slightly more efficient. Section 6. Heat death, the original apocalypse. The version of the ending we've just walked through, star formation dying out, black holes evaporating one by one, everything settling into cold, diffuse quiet, is exactly what that 1865 Clausius line was pointing toward. And it has a name of its own, Heat death, the oldest apocalypse in modern physics. Clausius wasn't the only one to reach this conclusion. Around the same time, on the other side of the English Channel, the physicist Lord Kelvin was independently applying that same second law to the universe as a whole, and reached almost the identical verdict, describing the universe's fate, in his own words, as a state of universal rest and death. The physicist Hermann von Helmholtz, working separately again, described a nearly identical future in which the universe would be condemned to a state of eternal rest. And Clausius himself, in other writing beyond that famous two-line summary, described the same endpoint as a state of unchanging death. It's worth pausing on that trio of names for a second, because none of them had telescopes powerful enough to see distant galaxies the way we can now, and none of them had any idea the universe was expanding. They reached this conclusion through pure thermodynamic reasoning, more than a full century before anyone had actual proof the universe even had a beginning at all. That's part of why heat death occupies such a strange, respected place within physics. It isn't some modern doomsday theory dressed up in impressive-sounding language. It's one of the oldest, most conservative predictions in the entire field, built on one of the single most well-tested physical laws we have. Here's the basic mechanism, in plain terms. Energy in the universe naturally spreads out and settles toward a uniform temperature, the same way a hot cup of coffee left sitting on a counter eventually cools down to match the room around it, rather than the room spontaneously getting colder while the coffee somehow stays hot. Once everything, everywhere, reaches that same shared temperature, there's no temperature difference left anywhere to do any kind of work. In the same way you can't run an engine off two objects that are already sitting at the exact same temperature. No temperature differences means no more stars forming, no more energy flowing anywhere in any organized direction, no more of the kind of structured activity that life, or any complex structure at all, actually depends on to exist. That final state, uniform temperature, maximum entropy, is what physicists mean by heat death. It's worth being precise about something the source material itself is genuinely careful about. Modern physicists distinguish between the strict, classical version of heat death, which technically requires the universe to reach a perfectly constant temperature absolutely everywhere, and what some researchers call cosmological heat death, a somewhat softer version, in which the universe's entropy, measured per unit of space, approaches a constant value, even while the universe as a whole never actually stops expanding and cooling. Because our universe keeps expanding indefinitely, it technically never reaches a perfectly fixed temperature, which means the strictest, most classical definition of heat death is, in a strange technical sense, avoided, even while the practical, observable outcome, a cold, dark, inactive universe, ends up looking almost identical either way you slice it. And here's something even more interesting than that. Heat death isn't universally accepted as inevitable, even today. A 2023 piece published in Noema magazine laid out newer interpretations of thermodynamics that leave the question considerably more open than the standard textbook version of the story suggests, partly because gravity itself behaves so strangely compared to ordinary, everyday thermodynamic systems. Gravitationally bound systems, like stars, actually have negative heat capacity, meaning they get hotter, not colder, as they lose energy, which is the exact opposite of how a cooling cup of coffee behaves. That single, genuinely odd property of gravity is part of why the universe has managed to build ever more complex, organized structures, stars, galaxies, planets, and eventually us, even while overall entropy keeps climbing the whole time. Some physicists argue that as long as gravity keeps finding new ways to concentrate energy locally, even inside a universe that's trending toward disorder on the whole, true heat death might function more like an asymptote the universe approaches forever without ever quite touching, rather than a fixed, guaranteed final destination. It's a genuinely unresolved argument within physics, not a settled fact, and that's worth remembering every single time you hear heat death described with more certainty than the actual research currently supports. Section 7. The Big Rip. Heat death assumes the universe simply keeps calmly expanding forever, at a rate that gradually slows, or at least stays roughly steady. But there's a second major possibility, one that doesn't end quietly at all, and it hinges entirely on a single unresolved number that physicists still haven't been able to pin down. That number is called W, and it describes the precise relationship between the pressure and the density of dark energy, the mysterious force currently driving the universe's accelerating expansion. Dark energy is estimated to make up roughly 68% of the entire universe's total energy content, which is a strange thing to really sit with. The single dominant ingredient of the cosmos is something we can currently only detect indirectly, purely through its effect on everything else around it. If W equals exactly -1, dark energy behaves the way a cosmological constant would, a fixed, unchanging background push, and the universe drifts steadily toward the slow, quiet heat death we just spent an entire section describing. That's currently the simplest working model, and the one most consistent with the measurements we actually have. But if W turns out to be less than -1, even by a small margin, dark energy stops behaving like a stable background constant and starts behaving like something physicists have taken to calling phantom energy. And phantom energy does something genuinely strange. Instead of thinning out as the universe expands, the way ordinary matter and radiation both do, phantom energy's density actually increases as space itself stretches further. More space means more phantom energy, and more phantom energy pushes space to stretch even faster still. It's a feedback loop, and once that loop gets started, there's no calming it back down again. Run that feedback loop forward far enough, and the underlying mathematics produces something called the Big Rip, a specific, finite moment in the future when the rate of cosmic expansion doesn't just become large, it becomes, quite literally, infinite. Everything gets torn apart at that point, and the destruction unfolds in a fairly intuitive order, working outward from the loosest bonds toward the very tightest. Galaxy clusters go first, pulled apart from one another. Then individual galaxies lose their grip on their own stars. Then solar systems come apart, planets slowly drifting away from their parent stars. Then planets themselves are torn apart, followed shortly after by the stars. In the very final fraction of a second, even atomic nuclei stop holding together. And finally, subatomic particles themselves are wrenched apart entirely, as each one becomes causally disconnected from literally every other particle in existence. According to one detailed model, the strong nuclear force, the force responsible for holding atomic nuclei together, and ordinarily the single strongest force in all of nature, is the very last thing to fail, giving way roughly 10 to the -19th seconds before the absolute end. How soon could any of this actually happen? That entirely depends on exactly how far below -1 the true value of W ultimately turns out to be. For a phantom energy model with W sitting at -1.5, a fairly aggressive but not remotely absurd value by the standards of theoretical cosmology, the Big Rip could occur in as little as about 22 billion years from right now, which, compared to almost every other number covered in this video, is remarkably, almost uncomfortably soon. Cosmologist Robert Caldwell, one of the researchers who helped originate this entire line of research, has mused that if the Big Rip really is our universe's ultimate fate, we might currently be living inside a kind of cosmic sweet spot, late enough that galaxies, stars, and planets have already had the time to fully form, but early enough that none of it has actually been torn apart yet. It's a strangely comforting thought in its own particular way. Not that the ending won't eventually come, but that we happen to exist in the narrow window where the universe has already finished building something genuinely worth noticing, and hasn't yet gotten around to destroying it. It's also worth saying plainly that plenty of physicists remain skeptical of the Big Rip specifically as a scenario. Cosmologist Paul Steinhardt and others have pointed out that most of the theoretical models actually capable of producing genuine phantom energy tend to run into serious internal problems and instabilities the moment you examine them closely, which is a large part of why heat death, and not the Big Rip, remains the currently favored default outcome among most working cosmologists today. Current measurements can't fully rule the Big Rip out entirely, but they don't particularly favor it either, at least not yet. Section 7.5, the live experiment, trying to answer this right now. Everything in the last section hinged on that single number, W, and here's the genuinely exciting part. Physicists aren't just theorizing about it from an armchair, They're actively out there right now, tonight, trying to measure it directly, and the results coming in over the last couple of years have been stranger than almost anyone expected. The instrument doing most of that work is called DESI, short for the Dark Energy Spectroscopic Instrument, an international collaboration of more than 900 researchers spread across over 70 institutions, mounted on a telescope at Kitt Peak National Observatory in Arizona, capable of capturing the light from 5,000 separate galaxies simultaneously. In March of 2025, the DESI team released an analysis built on their first 3 years of observations, covering nearly 15 million galaxies and quasars, the single largest three-dimensional map of the universe ever constructed, specifically designed to track dark energy's influence across the past 11 billion years of cosmic history. Here's what they found, and it's worth sitting with, because it directly touches the heat death versus Big Rip question we just spent an entire section on. Taken entirely on its own, DESI's data are still perfectly consistent with the simplest model, dark energy as a true, unchanging cosmological constant, W, locked at exactly -1. But once you combine that data with 3 other independent lines of evidence, the cosmic microwave background, distant exploding stars called supernovae, and the way gravity bends light from faraway galaxies, something strange starts to show up. Across multiple different combinations of these datasets, there's a growing hint that dark energy's strength might actually be weakening over cosmic time, rather than staying perfectly constant the way the simplest model assumes. Will Percival, one of DESI's co-spokespeople and a professor at the University of Waterloo, described the shift plainly. We're guided by Occam's razor, and the simplest explanation for what we see is shifting. It's looking more and more like we may need to modify our standard model of cosmology to make these different datasets make sense together, and evolving dark energy seems promising. His colleague Alexei Leothord-Harnett, co-spokesperson and a professor at UC Santa Cruz, put it this way: what we are seeing is deeply intriguing. It is exciting to think that we may be on the cusp of a major discovery about dark energy and the fundamental nature of our universe. Now, the honest caveat, because this is exactly the kind of moment where a story like this can get overstated. In physics, a genuine, confirmed discovery conventionally requires a statistical confidence level called 5 sigma. Depending on exactly which combination of datasets researchers use, this particular result currently lands somewhere between 2.8 and 4.2 sigma, real, and getting stronger with better data, but not yet at the level physicists consider a fully confirmed discovery. A 3 sigma result corresponds to roughly a 0.3% chance of being nothing more than a statistical fluke, which sounds convincing, and often is, but plenty of 3 sigma results throughout the history of physics have quietly faded away once more data came in. The researchers themselves are careful to frame it exactly this way. Seshadri Nadathur, a professor at the University of Portsmouth working on the DESI collaboration, said it directly. It's not just that the data continue to show a preference for evolving dark energy, but that the evidence is stronger now than it was. We've also performed many additional tests compared to the first year, and they're making us confident that the results aren't driven by some unknown effect in the data that we haven't accounted for. What makes this genuinely thrilling, rather than just another headline, is what it would mean if it holds up. Willem Elbers, a postdoctoral researcher at Durham University working on the collaboration, summed up the stakes. For a couple of decades, we've had this standard model of cosmology that is really impressive. As our data are getting more and more precise, we're finding potential cracks in the model and realizing we may need something new to explain all the results together. And DESI's director, Michael Levi, connected it directly back to the exact question this entire video has been circling. Whatever the nature of dark energy is, it will shape the future of our universe. It's pretty remarkable that we can look up at the sky with our telescopes and try to answer one of the biggest questions that humanity has ever asked. To be clear about where this leaves us, nobody on the DESI team is claiming to have discovered evidence for a big rip, or for heat death, or for any specific named ending. What they've found is evidence that the very simplest assumption, that dark energy is a fixed, unchanging constant, might not survive closer scrutiny, and that whatever replaces it will need to explain several independent datasets at once. DESI is currently in its 4th of 5 planned years surveying the sky, aiming to eventually measure roughly 50 million galaxies and quasars before the project wraps up, with additional experiments coming online in the years ahead to test these hints even further. This is about as close as you can get, in real time, to watching scientists try to figure out which of the endings in this video is actually the right one. And the honest answer, as of right now, is that they don't fully know yet, and they're telling you that themselves. Section 8. The Big Crunch. There's a third classic ending on the table, and it's essentially the mirror image of everything we've just walked through. Instead of expansion running away forever, what if it simply slowed down, stopped completely, and then reversed direction entirely, pulling everything back the other way? This is the Big Crunch, the idea that the universe's expansion eventually halts and reverses course, with gravity finally winning out over dark energy and pulling all matter and energy back together toward a single point, essentially running the Big Bang backward. For decades, this was considered a genuinely live possibility, hinging almost entirely on whether the universe contained enough total matter for gravity to eventually overpower the expansion. What would that actually look like if you were somehow still around to witness it happening? According to Katie Mack, it would come with plenty of advance warning, unlike some of the other endings on this list. You'd start to notice galaxies that had spent billions of years steadily receding, slowly beginning to approach instead. The night sky would gradually brighten as galactic light got compressed and blue shifted, and eventually the background radiation filling the universe would climb sharply in both temperature and frequency, growing harsher and more energetic by the day. Long before any actual collision took place, the sky itself would simply become unbearably hot, the entire universe behaving less like a familiar night sky and more like the inside of an oven, with the door slowly, inexorably swinging shut. Since the discovery in the late 1990s that the universe's expansion is actually accelerating rather than gradually slowing down, the Big Crunch has become the least favored of the major named scenarios among working cosmologists, since it fundamentally requires dark energy to somehow reverse its currently observed behavior. It hasn't been ruled out entirely, since our understanding of dark energy remains genuinely incomplete, but of all the major named endings, it currently sits furthest from where the actual evidence points. Section 9. Vacuum decay, the one with no warning at all. Now for the scenario Katie Mack herself has said is her personal favorite to think about, not because it's pleasant in any way, but because it's the strangest of the bunch, and because, unlike everything else covered in this video, it doesn't come attached to any comforting number of years. It starts with the Higgs field, the same field responsible for the Higgs boson particle discovered at the Large Hadron Collider, and the same field responsible for separating the electromagnetic force from the weak nuclear force in the universe we currently inhabit. Based on the measured mass of the Higgs boson, about 125.18 billion electron volts, and the measured mass of the top quark, about 173.1 billion electron volts, physicists have calculated that our universe's vacuum, the actual physical state of empty space itself, sits inside something called a metastable configuration. Metastable is a specific, genuinely useful word here. It doesn't mean unstable exactly, and it doesn't mean permanently safe either. Physicists sometimes compare it to a cup sitting near the very edge of a table, stable enough to stay put under ordinary, everyday conditions, but not actually resting at the lowest possible point it could theoretically reach. Somewhere out there, mathematically speaking, there exists a lower energy configuration for the Higgs field, a true vacuum, as opposed to our current false vacuum. And in quantum mechanics, systems don't actually need any kind of external push to eventually find their way toward a lower energy state. Given enough time, a single random quantum fluctuation, with no external cause required, no warning sign whatsoever, no gradual buildup of any kind, could be enough to tip a tiny region of space over into that true vacuum state. If that happens, a bubble forms. Inside it, the fundamental rules of physics are simply different enough that atoms as we currently know them, and everything built out of them, couldn't exist in their old familiar form anymore. That bubble would then expand outward, in every direction at once, at or extremely close to the speed of light. And because light speed happens to be the fastest anything, including information itself, can ever travel, there is no possible way to see it coming, ever. No telescope could offer any advance warning, because the bubble's leading edge would be moving exactly as fast as the light that would otherwise let anyone see it approaching. If it started right now, somewhere on the far side of the galaxy, we could, in principle, already be living inside the very last light of a universe that has, elsewhere, already ended. Physicist Sean Carroll has written about this directly, in language once summarized by a science blog this way: the Higgs potential has a worrisome feature, namely that it might become metastable at very high energies, and this could mean the universe is capable of undergoing catastrophic vacuum decay, with a bubble of true vacuum expanding outward at the speed of light, something that could happen at any time whatsoever, without warning. It's important to say exactly how that particular quote is meant to be read, though. Carroll wrote it in careful, explicitly conditional language, using words like might and could throughout, and physicist Matt Strassler, writing a direct rebuttal to some of the more sensational news coverage this idea generated at the time, was refreshingly blunt about the whole thing. "The Higgs boson is not dangerous," he wrote plainly, "and it will not destroy the universe. Nothing humans do, including operating the Large Hadron Collider itself, carries any meaningful chance of triggering this process. If vacuum decay happens at all, it would be an extraordinarily rare, entirely spontaneous quantum event, playing out on timescales that have absolutely nothing to do with human activity whatsoever." There's also a genuinely strange philosophical wrinkle some physicists have pointed to here, Sean Carroll among them, working alongside physicist Kim Boddy. If the universe really is doomed to an eternal, ever-expanding heat death, that eternal, extremely high-entropy future comes bundled with its own bizarre statistical problem, one we're about to spend an entire section unpacking properly. Some physicists have semi-seriously suggested that a universe with a genuinely finite lifespan, one that eventually ends cleanly through vacuum decay rather than stretching on forever, might actually represent the tidier, more physically sensible outcome, precisely because it avoids drifting into an eternity that eventually fills up with exactly this kind of strange statistical anomaly. It's a genuinely odd corner of theoretical physics, the idea that the total, sudden destruction of everything might, in a purely mathematical sense, be considered the neater and more elegant outcome. Section 10. The strange statistics of Boltzmann brains. That statistical anomaly we just mentioned deserves its own proper section, because it's one of the strangest, most genuinely mind-bending ideas connected to any of this, and it comes from a surprisingly old source. Ludwig Boltzmann was an Austrian physicist working in the late 1800s, one of the founding figures of an entire branch of physics called statistical mechanics, the field that explains heat and entropy in terms of the countless tiny particles doing the actual work underneath. In 1896, building on a suggestion originally floated by his own assistant, Ignaz Schütz, Boltzmann proposed something genuinely strange, decades before anyone had even conceived of the Big Bang. What if the low-entropy, highly organized universe we actually observe doesn't require a special beginning at all? What if it's simply an extremely rare, entirely random statistical fluctuation occurring inside a much larger universe that otherwise spends nearly all of its existence sitting in a featureless, high-entropy equilibrium? The modern version of this idea carries his name, the Boltzmann brain. Picture a universe that spends the overwhelming majority of its existence in a cold, high-entropy, near-heat death state, exactly the kind of state we've spent this entire video describing. Given a genuinely, truly infinite stretch of time, quantum and thermal fluctuations within that state will, eventually, and completely at random, assemble complex low-entropy structures out of pure statistical chance. And in principle, given enough time, that includes a fully self-aware brain, complete with an entire set of vivid, detailed memories describing a past that never actually happened, before that brain simply dissolves right back into the surrounding chaos moments later. Here's the actual paradox, and it's a genuinely serious one, not just an interesting thought experiment. Statistically speaking, inside a truly eternal universe, these randomly assembled Boltzmann brains would vastly, overwhelmingly outnumber brains that arose the ordinary way, through billions of patient years of stellar formation, planetary chemistry, and biological evolution, which raises an extremely uncomfortable question. If you genuinely can't be certain you aren't one of these randomly fluctuated brains, sitting there with fabricated memories of an entire life and an entire universe that never actually existed, what does that do to the reliability of any observation at all, including every single observation that built the whole of modern cosmology in the first place? Physicist Sir Arthur Eddington ran into a related version of this exact problem all the way back in 1931, framing it this way. A universe containing mathematical physicists, he argued, will, at any randomly chosen date, sit in the maximum possible state of disorganization that still happens to be consistent with the existence of creatures like that. In other words, Eddington recognized that Boltzmann's statistical framework didn't just technically allow for these rare fluctuations. It precisely predicted how minimally organized and how astonishingly rare they ought to be. Let's actually put some numbers on this, because the sheer scale of the odds involved is genuinely half the fun of the whole idea. Physicist Sean Carroll has estimated that assembling something as intricately ordered as a functioning brain, purely out of near-empty space, by pure random chance, requires an entropy decrease so enormous, roughly 10 to the 66th power in the relevant units, that the actual probability of it happening scales as e raised to the power of negative 10 to the 66th. That is a number so small that the phrase astronomically small doesn't come close to covering it. And yet, given the truly vast timescales involved inside an eternally expanding universe, where the characteristic recurrence time for events runs somewhere around e raised to the power of 10 to the 122nd seconds, even a probability that absurdly small would still eventually occur. And then it would occur again and again, infinitely many times over, given genuinely infinite time to work with. This isn't just an abstract philosophical curiosity that physicists enjoy arguing about over coffee, either. It's become an actual functional technical checkpoint used to test serious theories of cosmic inflation and the multiverse. Physicists now specifically ask, of any proposed model, does this particular theory predict that Boltzmann brains would vastly outnumber ordinary observers like us? If the answer comes back yes, most cosmologists treat that as a genuinely serious strike against the theory, since a model like that would quietly undermine the basic reliability of empirical observation that the entire enterprise of science depends on in the first place. It's part of why some physicists have suggested, at least semi-seriously, that a universe ending cleanly through vacuum decay, rather than drifting on forever into an eternity thick with these strange statistical accidents, might actually be the more internally consistent, more physically sensible outcome after all. Section 11. The Bounce, and Roger Penrose's Cyclic Universe. There's a fifth possibility inside Katie Mack's original framework, and it's the only one of the bunch that doesn't actually claim to be a true ending at all. It's called the bounce, and it proposes that whatever ultimately happens, whether it resembles a big crunch or something even stranger, the universe doesn't simply stop. Instead, it cycles. Contraction eventually gives way to a fresh new expansion, a new Big Bang of sorts, with the whole process potentially repeating itself over and over, without any true, final, closing chapter at all. The most prominent modern version of this idea comes from Sir Roger Penrose, a mathematical physicist at the University of Oxford and co-recipient of the 2020 Nobel Prize in Physics, awarded for entirely separate, widely accepted earlier work connecting general relativity, black holes, and gravitational singularities. Around 2005, and later detailed extensively in his 2010 book Cycles of Time, Penrose put forward a specific proposal he calls conformal cyclic cosmology, or CCC for short. The core idea runs almost exactly backward from the standard picture most cosmologists currently favor. Instead of the universe becoming smooth and uniform right after the Big Bang, the way conventional cosmic inflation describes it, Penrose proposes the universe actually becomes smooth and uniform at the very end of what he calls an aeon, an unimaginably distant future state in which every scrap of matter has eventually been consumed by supermassive black holes, and those black holes have, in turn, fully evaporated away through Hawking radiation, wiping out essentially all structural complexity across the entire universe and restoring a smooth, featureless, uniform state, not entirely unlike the smooth state cosmologists believe existed right at the very start. Here's the genuinely clever mathematical trick underneath the whole idea. Because that far future end state, infinitely large, infinitely diffuse, and the state of a brand new Big Bang, infinitely small, infinitely dense, can, under a specific mathematical operation called a conformal transformation, actually be treated as mathematically equivalent to one another. Penrose argues the ending of one aeon can be directly identified with the beginning of the next one, without requiring any actual physical contraction or literal bounce in the more conventional sense of the word. For this particular mathematical trick to actually work, though, there's a strict requirement. Every single particle in the universe has to eventually lose all of its rest mass as the universe grows extremely old, leaving behind nothing but pure, massless radiation. Penrose and his collaborators have gone as far as to claim they've found possible supporting evidence for this idea, in the form of faint circular patterns detected within the cosmic microwave background, which they interpret as potential echoes of black hole collisions carried over from some previous eon. It's important to be fair and clear here. This specific claim is genuinely controversial, and it has not been broadly accepted by the wider cosmology community. Other researchers examining the same data have been unable to confirm that these circular patterns represent anything more than ordinary statistical noise, and prominent critics have argued there simply isn't real evidence for a universe before the Big Bang, and that conformal cyclic cosmology hasn't matched the predictive track record and successes of the standard inflationary Big Bang model that most cosmologists currently favor. It's worth presenting this fairly and even-handedly. Conformal cyclic cosmology remains a minority, actively disputed position within modern cosmology, a serious, carefully worked out mathematical proposal from an actual Nobel laureate, but one that hasn't displaced the standard model, and one that has drawn substantial, published skepticism from other serious researchers in the field. It sits on the short list of real possibilities, not because it's currently winning the argument, but because nobody has been able to definitively rule it out either. Section 12. A different kind of question. Could anything survive? Everything we've covered so far has been about what happens to matter, energy, and space itself. But there's a genuinely different, and in some ways more hopeful, question that a handful of serious physicists have actually taken the time to work through properly. Even inside the bleakest of these scenarios, could some form of intelligence, some way of thinking and experiencing time, actually keep going indefinitely? In 1979, physicist Freeman Dyson, working at the Institute for Advanced Study in Princeton, published a paper in the journal Reviews of Modern Physics titled Time Without End: Physics and Biology in an Open Universe. Rather than asking how the universe ends, Dyson asked something quite different: whether intelligent life could, in principle, survive and keep experiencing an unlimited amount of subjective time inside an ever-expanding, ever-cooling universe. His conclusion, stated directly in his own paper's abstract, was genuinely striking. An open universe need not evolve into a state of permanent quiescence. Life and communication can continue forever, utilizing a finite store of energy if the assumed scaling laws are valid. The mechanism behind that claim is elegant. As the universe expands and cools toward absolute zero, the minimum thermodynamic energy cost required to process a single bit of information also drops toward zero, right along with it. Dyson argued that a sufficiently adaptable form of intelligence could deliberately slow down its own metabolism and its own rate of thought to match that falling ambient temperature, spending its finite energy budget more and more slowly as time goes on. Done carefully enough, that strategy would allow it, in principle, to complete an infinite number of individual thoughts across an infinite stretch of cosmic time, all while only ever drawing on a single, finite total amount of energy to begin with. It's worth being honest about the caveats here, because they're significant ones. Dyson's original scenario assumed what cosmologists at the time called an open universe, one that expands forever but gradually decelerates as it goes, which was a genuinely live cosmological possibility back in 1979. His paper was written almost 2 full decades before the 1998 discovery that the universe's expansion is actually accelerating, driven by dark energy, rather than slowing down the way Dyson had assumed. Later analysis, including follow-up work connected to Krauss and Starkman's own research, has suggested that this kind of accelerating expansion, the version we now believe is actually real, may genuinely undermine some of the key mathematical assumptions Dyson's original scaling argument depended on, since an accelerating universe behaves quite differently at extremely late cosmic times than the simpler, decelerating models Dyson was working with at the time. Even Dyson's own framework has a second, more theoretical wrinkle attached to it. If a civilization ever managed to master something called fully reversible computing, a real, if extraordinarily difficult concept within computer science and physics, it could, in principle, perform an unlimited amount of computation without needing Dyson's original strategy of progressively slowing down and cooling off at all, since truly reversible computation doesn't carry the same minimum energy per thought cost that ordinary computing does. It's worth being clear about exactly what this section is and isn't. Dyson's paper is a genuinely serious, peer-reviewed piece of theoretical physics, not idle speculation dressed up for entertainment, but it's also explicitly framed as a best-case scenario, an argument that only holds if the assumed scaling laws are valid, built on top of a model of the universe's expansion that we now have good reason to believe isn't quite the one we actually live inside. It's included here not as a settled prediction, but as solid evidence that serious physicists have thought carefully and rigorously about the question of survival and meaning, even while staring directly at the bleakest-sounding long-term forecasts physics has to offer. Section 13. Living inside the uncertainty. So here's where all of this actually leaves us. Physicists have laid out, roughly, 6 or 7 genuinely serious ways this could all go. A slow fade into cold, diffuse quiet that takes longer than a Google years to fully finish playing out. A runaway tearing apart that could, under the right conditions, arrive in a mere 22 billion years. A collapse back into a single point, an idea that's currently out of favor with most cosmologists, but not definitively ruled out. A silent, instantaneous rewriting of physics itself, one that could, mathematically speaking, already be racing toward us at the speed of light, this very moment. A repeating cycle with no true final chapter at all, according to a Nobel laureate's still disputed proposal. And, running quietly underneath all of it, the open, statistically uncomfortable possibility that consciousness itself, at any given moment, might be a random fluctuation rather than the product of an actual, coherent past. What's genuinely remarkable, sitting here in cosmological decade 10, barely a heartbeat into the universe's actual total lifespan, is how much of this we've actually managed to work out already. None of these predictions come from guesswork, mysticism, or storytelling. Every single number in this video traces directly back to a real measurement, the Higgs boson's mass, measured precisely at the Large Hadron Collider. The proton's lifetime, patiently constrained by decades of watching at Super Kamiokande, a full kilometer underground. The rate our own galaxy is closing in on Andromeda, tracked through the careful, painstaking measurement of a galaxy's tiny motion across the sky. Even the theoretical evaporation of black holes, an event so slow that not a single one has ever actually been observed finishing, still follows directly and predictably from combining 2 of the most rigorously tested theories physics has ever produced. And that, ultimately, is the calming part, if there genuinely is one here. This isn't a set of vague, mystical prophecies handed down from on high. It's an active, ongoing, working body of science. The same basic kind of science that gives us weather forecasts, vaccines, and the very device this video might currently be playing on, just aimed at a far longer horizon than we're generally used to thinking in. The scientists building these models keep revising them the moment new evidence comes in, the same way the Andromeda collision odds shifted from essentially certain to roughly a coin flip the instant better simulations became available. The same way Earth's odds of surviving the Sun's expansion shifted the moment someone modeled the underlying tidal forces more carefully. Nothing here is carved in stone. It's a living, constantly evolving picture, built patiently over generations by people who spend entire careers narrowing down exactly how much time and what kind of ending we're actually looking at. And underneath all of it sits one quiet, genuinely reassuring fact worth holding on to. Every single pathway we've walked through tonight, even the fastest one, even the Big Rip running at its most aggressive, plays out across a scale of billions of years, at an absolute bare minimum. The slowest of these endings stretches across a number so large it needs the word Google just to be written down comfortably at all. Whatever eventually happens to this universe, it is not going to happen to you, or to anyone alive today, or to anyone's grandchildren, or to anyone's grandchildren's grandchildren, repeated so many times over that the phrase quietly stops meaning anything useful at all. We happen to exist inside an almost unimaginably early, quiet, stable moment in the life of a universe that is, by any honest measure available to us, just barely getting started. That's the calm science of the end of everything. 6 or 7 genuinely real possibilities, each one grounded in actual measurement, each one still being carefully refined, and every single one of them so far off in time that the only truly sensible response, once you actually sit with the numbers properly, isn't fear at all. It's a strange, settled kind of peace. If this is the sort of thing that helps you sleep rather than keeps you up, you already know what to do. Like this video, subscribe for more of exactly this, and we'll see you in the next one, somewhere out at the far edge of what we currently know.